Let's talk about a recipe for a coordinate system. First, we need the datum, which I don't have up here. We talked about that. So the datum sets the stage of where you are on the planet. It has a Latin long value associated with that. Then we need, sets the point of origin. Sorry, that's the last point right here. This is based on the horizontal datum, like North American datum 83. That point of origin, we assign a 0, 0 value. That's going to be 0, 0 for this gridded projected coordinate system. We have a projection, which is either a cylinder, a cone, or a plane, typically. There are some more complicated ones. And then with that projection, we get a Cartesian coordinate system, which is just X and Y. So we have X and Y, northing, easting. X is easting, Y is northing. And you can see that everything is pointed in the east direction and the north direction. So the point of origin is typically going to be west. Sometimes it's going to be southwest of the area of interest. And in this case, this is the state of Washington. And so everything's going to be either north or east of that typically. That's why we say northing and easting. So that just means the point of origin is always going to be on the left-hand side of your coordinate system. And that's simply just standard of practice. So to minimize the possibility of using negative coordinate values, a false northing and easting are added to that 0, 0. And so maybe we start out at 100,000, 100,000 or something like that, right? So that's a false northing and easting. It's just added to 0, 0 so that we have kind of big numbers to work with. And then we have a scale factor, and we'll talk about that later, but that's applied to reduce distortion when we go from a gridded plane to the moving, lumping ground. And we'll get into what scale factor is later, but it's typically less than 1. It's usually like 0.9, something like that. So let's look at a coordinate system. This is a projected coordinate system for Mesa County. And actually within Mesa County, there's a bunch of different zones. Why would we want a coordinate system with multiple zones for Mesa County? Why is that a thing that even exists? So elevation can be important, and we'll talk about that when we talk about the scale factor. If you, for example, I'm surveying down here in the valley, do I want the same coordinate system as I might use on top of the mesa? And the answer is no, because when you get elevation, I'm basically fitting a flat area to the bottom of the Grand Valley, right? Versus something that's going to be way over there. And if I'm surveying off the same flat area that's 6,000 feet different in elevation from the mesa, there's going to be a lot of distortion and error from the coordinate system that I'm measuring up there versus if I were using the one down here. So this is broken up. The more local your coordinate system is, the more accurate it's going to be, the less error in terms of X and Y, and as well as Z. So you can see that the point of origin has a Latin long value, and that's going to be likely based off of North American datum 1983. So we know where that point is on the surface of the planet, or the ellipsoid in this case. We have a false northing and a false easting, so it starts at 50,000 and 100,000. Then we have a scale factor. And that essentially, there's this other thing that we'll talk about later, but that essentially are the nuts and bolts of this particular coordinate system. Also note that it says transverse Mercury projection. So that is the, let's see, go back here. Here's the Mercury. So that's a cylindrical projection. So we have a projection, a point of origin, a horizontal datum, which is tied up into these coordinates, a false northing and easting, and then a scale factor. And then Mesa County has broken this up based on elevation and just location. They've broken up the coordinate system based on that. Actually, this is beyond Mesa County, but it's all for this kind of western slope area. So here's the state plane system. And what the state plane system does is break our country up into projected planar systems, usually based on feet or meters. I guess the state planes can mean meters. And each state typically is divided up into multiple areas. Some of them aren't. You can see North Carolina. Some of these smaller states just have one. And like we said, the more local your coordinate system is, the less error you have in mapping what's on the gridded space versus what's on the ground. So Colorado, you can see, has 3, and these are going from east to west. So that means they're conic. Remember, the cone is really good for doing these long strips. The north and south ones are going to be cylindrical. And then there's some oblique ones. I think those are for maybe Alaska or something like that. That's just a plane, basically, or maybe, it says Mercury, so that's probably just a cylinder that's at an angle, essentially. So these are the state plane systems. You'll hear state plane a lot. It's kind of a standard one that engineers use when mapping and surveying. And we have Colorado North, Central, and South. So why did we break Colorado up into 3? Why not just 1? Yeah, yeah. Yeah. Honestly, that's a great argument. So the idea that why don't we split up? We have the kind of the Rocky Mountains, which have high elevation, kind of like what Mesa County did, right? Then we have the plateau, Western Colorado, and then the plains. Honestly, to me, that makes more sense, but this is the way they decided to do it. And really, it was just a decision. Colorado is longer than it is taller. And because of that, they did these strips from east to west. But you're right. So that's why it's good to know, well, if I'm doing a survey or I have GIS data in this, say, Colorado South, I'm probably going to have, there's going to be a trade-off in accuracy because you're trying to fit it to the whole state, which has the Rocky Mountains and the plains. So it's not going to be super accurate. It's going to be fine for kind of mapping scale. But if you think about surveying, maybe you want to be using like a local Mesa County coordinate system, right? Which is going to be much more accurate. So the idea for the state plane coordinate systems is we want to maintain XY accuracy of 1 part in 10,000. And so that means as we go from, say, over 10,000 feet, we want it to be accurate within plus or minus 1 foot, and that's in the X and Y direction. So that's the standard here, and you can decide based on data quality needs if that's appropriate or not. Here's the UTM projection or coordinate system. So 60 zones across the globe at these Latin long values, and we have this Mercator cylindrical projection for each zone. Units are always in meters, and Colorado is mostly in UTM zone 13, but there's a little sliver in 12 you can see right here. And so actually Grand Junction's in UTM 12. All right, to summarize, we have geographic coordinate systems. These are unprojected, they're spherical or ellipsoidal. WGS 84 is one of those. We have latitude and longitude numbers. We can then project onto a plane. We have X and Y now, meters or feet, easting and northing. State plane is an example, UTM is an example. The Mesa County coordinate systems are an example of projected coordinate systems. In GIS, you can see this information. It's usually at the bottom. You can click on this down arrow and actually change. So it doesn't matter what the data are, the GIS data are. You can always change the where you move your cursor to read either Latin long, northing or easting or something like that. But you'll do some exercises where you'll like check what's the projection or what's the coordinate system of my map. And that can be different than the data. You can have data with multiple coordinate systems, but it's all going to be plotted in the map in a certain way. Here's a projection file. So if you look at a shape file, it might have up to 1, 2, 3, 4, 5, 6, 7 files associated with this same GIS file. You can see it has the same name, just a different, what's this called? File type. So the .prj file is really just an ASCII text file, and it has all this information in it. So I want to know what projection my shape file is. I can click on this, open it up in Notepad, and it'll say, okay, here's the projection name right here, NAD 83, so North American datum. HARN is some update on that. UTM zone 12N. All right. So it's a UTM. We know it's in meters because UTM is always in meters. It tells you the geographic coordinate system, North American, 1983 HARN. Here's the datum. It's really the same information, NAD, high accuracy reference network. That's what HARN stands for. So that was an update to the 83. Here's the spheroid. So it's a spheroid with this information associated with it. Here's your prime meridian, units of degrees. That's all for the datum. Now we get into the projection. It's a transverse Mercury projection. Here's a false easting and northing. The central meridian, the scale factor, latitude of origin, and then units, horizontal units. So these are all the pieces of information you need to create this projection. So that's a shape file, right? A vector type of data. Here's a raster. This is a TIFF file. And there's actually two pieces of information. This is a TIFF world file. And here's the projection. These both work together to give rasters georeferenced information. So a raster has multiple files as well. This is the image, just the normal .tiff is the image itself. And then these are the information that tells you where to plot it in space. So in ArcGIS, you can set the coordinate system for your map. And usually if you bring in a shape file, it'll set the coordinate system for the map based on that first shape file that you bring in. So you drag that shape file in or load it, and then all of a sudden the map sets the projection in the coordinate system. You can also change it by right-clicking on map, going to properties, and then coordinate system. And then you can choose it yourself as well and just set it for what you want it to be. There's going to be many versions of a particular projection, so it can be very confusing. Usually you just want to stick with one and make sure you're sticking with that. So there's NAD 27, NAD 1983, updated in 2011, right? Here's one that was updated in 96. Here's the HARN one, right? Here's the original 1983. So each of these horizontal datums is going to have a state plane associated with it. I like to use the most up-to-date one when I project data. So that would be 1983, updated in 2011. And then you have your state planes within that horizontal datum. Okay, so we'll do this exercise together. We got about 15 minutes. So go ahead and get on your computers and we'll do a walkthrough of basically taking some unprojected data, and ARC will plot it in a funny place. And then we'll figure out how to set the projection so that it plots where it should be, all right? If we have multiple coordinate systems on one map and one of them does not have a projection that's been defined, then the data will not overlap. And so we have to use what's called the define projection tool to do that. And so I'll just overview it real quick. We go to Tools, Geoprocessing, and then we search for Define Projection. We put in the unprojected data, and all it means is it does not have a .prj file. The data does have coordinates, it just doesn't have, ARC can't read and understand where those coordinates should be. So you bring in the data, you tell it what the coordinate system should be based on some detective sleuthing, and then it will do that for you. Just real quick before we do that, defining a projection is just telling ARC GIS that this is what the projection and coordinate system is for a particular shapefile. The shapefile already has a coordinate system in it. All the vector data has XY values. This is just creating that .prj file so that ARC can read it and know where to plot it. That's different from projecting data. And projecting data is typically going from one projection to another, or one coordinate system to another. So we can take a file that has WGS84, Latin long, and then we can use the project tool to translate it to state plane or something else. And so here's some examples. We can go from UTM to state plane. We can go from state plane central to state plane north. You can go from really any coordinate system from one to the other. And the reason why we might want to do that is because it's best practice to have all your data for a particular map or project in the same coordinate system and same projection. So you're often going to have multiple data sources. Maybe some of them are UTM, some of them are Latin long, some of them are state plane. It's good to have everything the same so that we have the best level of accuracy when we start to bring those data together, do analysis together. So that's the project tool. We bring in the data set. You give the name of the output data set. And so you can also do this for rasters. There's two different tools. So one is for vector data and one's for raster data. Okay, so for this class exercise, there's a tutorial called Projections and Coordinate Systems. We'll download the projections.zip file from module 2 in Canvas, and they'll do the tutorial together.